So, good morning. Last time I was talking about diffusion through a spherical pellet, and we have discussed this thing that the flux, that is moles of a in or flux into area of cross section, which is 4 pi r square for a differential section of the cell, and that is 4 pi r square at evaluated at r. As I said, we consider inward, which is generally the diffusion from outer to inside cell, but we are taking the direction outward, right. So, inward input is at r, which is basically one can write minus of that flux also. So, W a r into 4 pi r square minus the flux at r plus delta r, that is the whole thing evaluated at r plus delta r, and minus disappearance because of chemical reaction. So, we have defined here rate of reaction per unit mass of the catalyst. So, multiplied by the mass of the shell. So, 4 pi r square times delta r, that is the volume of the shell multiplied by the density of the catalyst pellet, right. So, that is the differential equation, and if you are simplified, you simplify the equation, then that comes out to be something like what we discussed last time of this form, and that has been discussed, right. So, for any nth order reaction, one can write minus R A is equal to K C A to the power n, and that differential equation is in the form of this K times C A to the power n, and we have divided by the diffusion coefficient. So, finally, the differential equation can be written either in this form or for nth order reaction it is in this form. Now, the solution, as I discussed, can be done numerically, right, using the mathematical tools, or analytically. Just a typical solution we were discussing for analytical. So, we discussed some dimensionless parameters, and that was defined like this, what we discussed last time. So, quickly I will go through that we defined a dimensionless concentration, which is defined as psi C A by C A S, that is concentration of the reactant species at any point inside the shell, and C S is the concentration at the surface of the catalyst. So, when you say R is equal to capital R, C A is equal to C A S concentration at the surface of the catalyst. Lambda, a dimensionless radius, which was defined the radius at any point divided by the total radius of the pellet. So, that was the lambda. And boundary conditions, we defined R is equal to capital R, C A is C S, and R is equal to 0, that is center of the pellet. C A cannot be infinite, right. So, if the equation say that the C A is infinite, it means the constant of the parameter has to be 0, right. So, C A has to be finite, because concentration decrease from outer to center of the cell, right. So, we just converted these dCA by dr and d2CA by dr square values in terms of these dimensionless parameters, and I discussed that by chain rule. So, dCA by dr is equal to dCA by d lambda into d lambda by dr. So, we defined that here in terms of dCA by d lambda, because we have already defined here. So, one can very easily define dCA by d lambda, and that is written here in the form of further extension d psi by d lambda, because psi is related to concentration times dCA by d psi into d lambda by dr. So, d lambda by dr can be calculated from here, and dCA by d psi can be calculated from here just by differentiation of this equation, right. So, we substituted that value, and finally, the expression was dCA by dr is equal to d psi by d lambda, which is now a parameter in the form of dimensionless concentration and the radius dimension, right, and times C S upon R, which is the differentiation from here and differentiation from here. Then we evaluated the second derivative d2 C A by dr square, and that is again defined d over dr of dCA by dr, that we discussed last time. So, one can again write d over dr in the form of d over d lambda into d lambda of dr. So, dCA by dr is calculated here. So, substitute it here in this equation, and finally, you have d2 psi by d lambda square, a second derivative of d psi by d lambda divided times the C S upon R square, right. So, that we have seen and discussed last time. So, using these dimensionless form, we developed the equation in this form, which is d2 psi by d lambda square plus 2 divided by lambda d psi by d lambda minus we have the term which is k1 r square divided by d e times psi, because we have divided the term all the term here and taken together. So, that became here k 1 r square times d E, which is a kind of parameter, and we have defined it as a Thiele modulus. So, it is the property of the pellet, right, and it is a property of the reaction also in fact, because order of reaction may affect this value, right. So, that we will discuss in detail later. So, for any nth order reaction also the similar form of the equation can be developed. So, that is shown here. So, in order to solve this differential equation now, so very quickly I will just go to this, that we try to convert this equation in a simplified form, right. That is the standard form for analytical solution, but if one can use Bessel functions also for solution, analytical solution, or one can go with the numerical technique as I discussed finite difference methods, right. So, we defined a parameter which correlated psi and lambda together. So, y another parameter which is psi into lambda. So, psi can be defined by y by lambda from here, right. So, one can very easily write the value of d 2 psi by d lambda square and d psi by d lambda in the form of y, right. So, you see here that d psi by d lambda is 1 by lambda times dy by d lambda minus y by lambda square. So, differentiation of this psi is equal to y by lambda, where y and lambda both are variable, right. So, you know the differentiation of this kind, first function differentiation of second minus second function differentiation of the first, right. So, 1 by lambda will give you lambda square, right, and minus lambda square, and same thing for this dy. So, first function 1 by lambda differentiation of y, so dy by d lambda, and minus second function, that is your this y, and differentiation of the first is 1 by lambda square. So, that is shown here. Now, do the second differentiation of this. So, one can very easily find out the value, and d 2 psi by d lambda square just again differentiated again. So, 1 by lambda differentiation of this, right, then dy by d lambda again differentiation of this second function, right, and whatever same thing here for the differentiation of the third function, right. So, one can very easily do this differentiation. So, now just if you substitute the value here in this equation, which is now a combination of the two terms d 2 psi by d lambda square and d psi by d lambda. So, finally, the equation is written in this form, which is d 2 y by d lambda square minus phi square y is equal to 0, and this equation has very standard format of solution, right. That is, this can be solved, just either you write in the form of hyperbolic function, right, which I discussed, or in the power of exponential form, right. So, d 2 y by d lambda square minus phi square y, this is a form of differential equation need to be solved for y or psi, right, psi as a function of y. When we write finally y is equal to psi into lambda. So, you can get the expression in the form of psi and lambda, right. So, this equation simply what we discuss for a pore. So, again I will just discuss to recall that how did we observe that in the pore of a catalyst, that the same equation we derived last time for a pore also, right. That is, that time d 2 C A by d z square minus k by d times C A, similar equation here, right. And the solution of this kind of equation can be written in this form also, or in hyperbolic function form, right. So, from this C A is equal to, which I shown in the other form, a times e to the power m into z, where m is square root of k by d, this term, right, and L times square root of k by d is the Thiele modulus again for the pore, right. So, this is for a pore, but we have done a cylindrical pore model and diffusion in that pore, right. So, the equation is similar. So, C A is equal to a times e to the power m into z plus b times e to the power minus m into z, and one can write it in the form of phi also, right, because m into L is your phi. So, phi is m into L, where L is this length of the pore, right. So, you can write here in the form of phi z upon L, and here minus phi z divided by L. And the solution of this equation now, because I told you that it is a very standard format, either you write in this form or you can write here a cos hyperbolic phi z by L plus b sin hyperbolic phi z by L, which is shown here in this form, right. So, solution based on boundary condition, because z is equal to 0, C A is equal to C A S at the pore mouth. So, here the concentration is known at z is equal to 0, right. Same thing there, we have written that at r is equal to capital R, C A is equal to C S, right. So, r is equal to capital R means lambda is equal to 1, right. So, C A by C S is 1 there, which is psi. So, if you solve this based on these two boundary conditions, then second is your z is equal to L, second boundary condition z is equal to L, nothing can move here, the pores are closed, pore is closed from this end. So, here d C A by d Z is 0, right. There we said at the center the C A is finite, one can write d C A by d R is 0 also because of symmetry, right. So, this equation which is now second boundary condition d C A by d Z is 0 at z is equal to L. So, you have two equations, two unknowns. So, A is C S e to the power minus m L divided by e to the power m L plus e to the power minus m L. You need to solve these two equations. So, one is that C A is equal to C S at z is equal to 0. So, this becomes A plus B, this is 1, this is 1. So, A plus B is equal to C S, right. And second time when you are writing z is equal to L, d C A by d Z is equal to 0, right. So, differentiate this equation for d C A by d Z. So, that will give you simply A m e to the power j m z minus b m e to the power minus m z, right, is equal to 0, put z is equal to L there. So, that will become second equation, right. Solve these two equations. So, if you solve them, then A is equal to C S e to the power minus m L divided by e to the power m L plus e to the power minus m L, right, and B is equal to C S cos e to the power m L plus divided by e to the power m L plus e to the power minus m L. If you remember your hyperbolic functions, this is nothing but e to the power m L plus e to the power minus m L, right, divided by 2 is your cos hyperbolic function, right. So, e to the power theta plus e to the power minus theta is your cos hyperbolic function, not 2 here I think, right. So, and same thing sin hyperbolic theta is e to the power theta minus e to the power minus theta. So, one is your cos function and one is your, if it is minus sign, that is sin function. So, here these are cos hyperbolic function, right. So, this is what you have seen here in the form of equation, either you write in this form or you write in the form of exponential, right, both are same thing, right, because the definition of cos hyperbolic theta or sin hyperbolic theta can be substituted. So, cos hyperbolic theta is e to the power theta plus e to the power minus theta, sin hyperbolic theta is e to the power theta minus e to the power minus sin minus theta, right. So, that if you substitute here, so this gives you C A by C S is equal to e to the power m times L minus z plus e to the power minus m L minus z. So, that term now A plus B values have been substituted, divided by e to the power m L plus e to the power minus m L, right. So, this is your what I said earlier, this is e to the power m L plus e to the power minus m L, this is your cos hyperbolic function, right. Same thing here, this e to the power m into L minus z plus e to the power minus m into L by z is cos hyperbolic m of this function, right. So, that has been written in the form of hyperbolic function, and m into L I told is phi Thiele modulus. So, cos hyperbolic phi L you take out. So, m into L is phi. So, cos hyperbolic phi 1 minus z by L divided by cos hyperbolic phi. So, this is the expression for concentration profile in a pore, right, C A by C S. So, if you look at this profile, C A by C A S versus if you plot Z by L in the pore of that. So, the concentration will drop like this, right, and if your phi is very high, it can go like this for increasing value of phi in a pore, right. So, what then mean high value of phi mean? High value of phi mean that means it mean that the reaction is strongly affected by diffusion resistance, right. So, phi value if high, then you can see here the concentration inside the pore drops faster, right, and this simply says that if you have a pore like this and if diffusion is dominating, it may happen if the concentration here is C s and at this point it becomes 0 at some value of Z by L, thus concentration is 0 here. So, it means this section is not being utilized properly, right. There is no reaction because no concentration here. So, it means that is very important when you look at the concentration profile. What you want if the high rate you want, then concentration should be uniform everywhere, right. If the resistance is not dominating, then this concentration should be uniform throughout the pore, right. So, that is when there is no diffusion resistance, phi approaches to 0. So, this is the interpretation of phi value, that is diffusion dominating reaction will have high value of phi, which simply says that your concentration gradient inside the pore is very high, right. So, this is for a cylindrical pellet. So, same thing is for the spherical cylindrical pore and then now it is for a spherical pellet, because same equation you got here. So, solution can be written in the form of either e to the power phi lambda plus e to the power minus phi lambda with these two constants, right, or you define it in this form, right. So, in that case if you look at here, now boundary conditions have been substituted for finding out the value of A and B, that at the center of the pellet, right, that is center of the pellet r is equal to 0, in other way lambda is equal to 0, right, other terms. So, your cos hyperbolic phi lambda will be 1, right. So, lambda is 0, cos hyperbolic 0 approaches to 1, right. If this and sin this 1 by lambda will be approaching to infinite, because lambda tends to 0. So, this is very high, right. So, you have two terms here in this equation, sin hyperbolic phi lambda is 0, right. So, this is 0. So, here you have 1 by lambda and lambda tends to 0, it says that this value is infinite, right. And I told you that at the center of the pellet the concentration has to be finite, right, low concentration. So, it means this constant has to be 0, right. This is the first interpretation from the boundary condition. So, this now equation is left only with this term, second term, right, because this is 0. Now, same thing for second, apply that. So, at psi is equal to 1, which is your outer surface of the solid, Ca is equal to Cas. So, psi is 1 and that time lambda is equal to r by r. So, r is capital R. So, lambda is 1, right. Substitute it here now. So, you have the value of B. This is y is equal to psi lambda. So, your y is 1 basically here. So, your B will be 1 upon psi sin hyperbolic phi, right, for lambda equal to 1. Substitute these two values here in y is equal to psi lambda, right. So, you have now the expression for concentration profile in the spherical pellet, right. Psi, which is defined by Ca divided by Cs, so y is psi lambda. So, that has now been written in the form of psi Ca divided by Cas, that is the concentration at any point, divided by the concentration at the surface, and that is equal to 1 by lambda. In the bracket you will have sin hyperbolic phi lambda divided by sin hyperbolic phi, right. So, this is the expression for spherical pellet concentration profile, and you have already seen this expression based on cos hyperbolic phi 1 minus z by L divided by cos hyperbolic form. So, that is in cos hyperbolic function, right. So, this is the concentration profile in a pellet, a spherical pellet. So, the significance of Thiele modulus, which I have already talked, but if you look at in detail, the Thiele modulus term for any nth order reaction, I define it for a first order reaction in a pore. So, phi is L under root of k by d, this is for first order, right, in a catalyst pore. Now, just try to understand these terms. If you look at, if I write it in the form of phi square, right, which will be L square times k divided by d, right. Now, if I try to write it in the form, because K is the rate constant, first order rate constant here, right, and based on volumetric unit. So, if you just look at, if I multiply here with pi r square times the L, that is now the volume of the pore. If I divide it by the same thing pi r square L, there is no change, right. So, this is now this K, and if I just again multiply just for further understanding C A concentration, right, and here also I just multiply by concentration, basically a surface concentration, which will be a something constant here, right. So, now try to interpret the terms. So, what you have left? So, L I can remove from here and I can take it in this. So, 1 L goes like this, right, pi r square can be cancelled. So, basically what is this term? This is your rate, kinetic rate, which is K times C A, right, and I multiplied the terms which is pi r square L. So, total rate, right, pi r square into L is the volume of the pore, and K into C A is CS is the concentration at the surface, right. So, that is basically representing the rate of reaction, right, kinetic term, a kinetic rate. In the denominator, dE dCA by, that is dE CA over L. If I write it, d times CAS minus 0 divided by L and multiplied by pi r square, which is here, right. So, that is flux, this is the flux, dCA by dZ, what you wrote earlier, right, dE dCA by dZ. So, this is basically diffusion flux, and multiplied by this pi r square, that is total moles which have been transported because of diffusion, right. So, this is a kinetic rate numerator and denominator is a diffusion rate. So, what is your Thielemans modulus square? Phi square, if you say for any first order reaction or any general reaction, now it is kinetic rate divided by diffusion rate. Right. So, the definition of Thielemans modulus square, that is phi square, is defined as the ratio of kinetic rate divided by diffusion rate, or in other words I can say it, because 1 upon diffusion rate is nothing but diffusion resistance, right. So, diffusion resistance divided by kinetic resistance 1 upon K, which is indicating the kinetic resistance. So, basically, or if you look at the definition of Thielemans modulus, it gives you the idea about which term is dominating during reaction, whether kinetics is dominating or diffusion is dominating in a reaction. Same thing, this is for one pore of a catalyst, and same definition is extended for any nth order reaction, because for first order you observed it K, right, C to the power 0. For if you do it the same expression, write it for second order reaction, then you will have here C. If third order, right, it becomes 2. So, in general this rate term phi square, basically a phi square, that is K n r square times C A S to the power n minus 1, that is the general expression now for any nth order reaction. What is written here? Divide by dE, diffusion coefficient, right. So, this has been just shown here, just like what we discussed in this case, multiplied, or you just take 1 r in the denominator. So, K n r C A S to the power n multiplied by the concentration and divide by the concentration. So, d E C A S minus 0 divided by r, diffusion flux multiplied by the area, if you write, that will be 4 pi r square in this case, right. And in the numerator also, if you define rate based on surface area, you will write down the same surface area, right, 4 pi r square for the pellet. So, again this definition says it is a surface reaction rate divided by a diffusion rate, right. That is again the similar definition what you have seen. And now, phi gives you the idea about the concentration profile in a pore, right. So, if diffusion is dominating, that is means the phi is large, diffusion resistance dominating means your diffusion coefficient is very small compared to the kinetic term, that is the numerator term. If your reaction is governed by diffusion, so you know the rate is controlled by slowest step of the reaction, right. So, if this is the case, slowest step of the reaction is suppose diffusion, right, it means its diffusion coefficient is very low, right. In that case the phi value will be large. So, generally it is said that for pellet, spherical pellet, if phi is more than 10 or more than 15 or 20, then diffusion is the rate controlling step, right. So, one can check by, because it depends on the R, capital R, radius of the pellet, right. It also depends on the concentration. When the positive order reaction, right, reaction is positive order and concentration is high, then the diffusion may be dominating, that is right. You have to check that, and rate constant will be a function of temperature, right. So, it means at high temperature it may be possible that kinetics is not controlling. So, diffusion may be rate controlling, right. So, these things can be looked into while doing the experiment, and one can check the effect of each process parameter, right. So, for large phi value means internal diffusion limits the overall rate of reaction, that is diffusion controlling reaction, and phi if small, this means that the surface reaction or kinetics controls the rate of reaction, and one can see here the concentration profile. If phi is small, then it is uniform concentration throughout the surface of the solid, the concentration will be uniform. So, you will have a higher rate there in that case, right, if it is a positive order reaction. In this case, if the medium, then this drops like that. If phi is very large, you see that this is the center of the pellet and this is the outer surface. So, the concentration change from C s to a final value 0, where the phi is increasing like this, right. So, very useful information one can get by understanding these effects. C A by C S we have already defined 1 by lambda sin hyperbolic phi lambda divided by sin hyperbolic phi. Once this is known, so one can get the idea how much rate is lowered because of diffusion, right. That is the I said that when there is a diffusion resistance, the rate will lower down, right. How much, what contribution is the diffusion resistance, right. So, one can very easily find out that the definition of a term, another parameter or very parameter of the catalyst, which is known as internal effectiveness factor. So, here I am saying internal world because it is into the pore of a catalyst or in the solid material, diffusion into a pore of a spherical pellet, right. So, the definition of effectiveness factor, it simply says that actual overall rate of reaction divided by the rate of reaction that would result if entire surface were exposed to the external pellet surface condition, right. What does it mean, right? The definition wise it is very clear now here that eta is given minus R A divided by minus R A S, right, like this disappearance of A which is actually happening and divide by the maximum possible rate of reaction, which is measured based on surface concentration or surface conditions, right. This can be defined based on surface area, based on per unit volume or mass of the catalyst, that has no meaning, right, that is similar. So, if you look at again here for the pore of a catalyst. So, now eta is global rate, I will say now, divide by intrinsic rate. Intrinsic rate. So, either you say global rate or you say observed rate or you say overall rate, right, all terms have same meaning, right. So, global means observed rate, what you look actually, right, when you do the experiment you will get this is your observed rate. Intrinsic rate is basically a maximum rate in one, I will just little bit change my sentence later, but right now I am saying intrinsic is the maximum rate which is measured at the surface condition, right. So, this is measured at the surface condition. So, basically for isothermal condition this is maximum, right, but when the reaction is non-isothermal and exothermic, then this may not be the maximum. I will discuss that later, but this is your general definition that it is measured under the surface condition, right, or surface condition, which is the maximum one. See, now look at the picture. If you here this picture, which is a spherical catalyst, and here we have written the concentration CAS, right, and this concentration profile is changing because we have the concentration profile for Ca by CAS, and that went down something like this, right. So, this is your R by R, which I have written now from this side. So, at the surface R is equal to capital R here, and then this is to the center. So, 0, right. So, if you need to calculate the rate, which concentration you will take, right. So, it means you have to divide it into differential zones, assuming, right, something like that what you integrate, and for that differential section calculate the rate and then integrate it for the whole pellet, right. So, it means something which is to be done based on the rate at differential Ca value, right. Suppose you are writing Kca here and then integrate it, right. So, Kca for the differential cell, right, which is you know now that you have already done that expression. So, if it is for whole pellet, it will be 4 by 3 pi r cube into K times Cs if I say first order reaction, right. But if you write it like this, then for a differential shell of that sphere, that will become 4 pi r square delta r, right. So, basically it this rate which you are calculating for a differential section is simply 4 pi r square delta r or dr into Ca. So, what will be total rate? Integrate this for the whole pellet. So, 0 to r, right, and 4 pi r square delta r times minus R A, right, that is for a spherical pellet. So, that will be your actual rate which you have gotten, because you know the concentration drops like this. But what will be this? Because you are saying it is the maximum rate, right. Maximum rate means it when the concentration. So, in one way you are saying there is no gradient of concentration. So, maximum rate will be based on this concentration. When you are assuming, because right now concentration drops, but maximum I say, it means the concentration is Cs throughout, measured based on the surface concentration, right, or in one way I am measuring the rate at the outer surface of a catalyst pellet, right. So, that will be simply your 4 by 3 pi r cube times, if I assume it is a first order, and Kca s. This is your maximum rate intrinsic which I said, right. So, global rate divided by intrinsic rate, that is your effectiveness factor, and for this you have to integrate this expression which is 4 pi r square delta r, right. For doing that, just I have shown you for the pore first, which is again the same thing. For a pore of a catalyst, this effectiveness factor is again the actual rate, right, divided by the intrinsic rate. So, actual rate which is based on some average concentration Ca bar, right. How will you find that Ca bar? By integrating the, that is overall throughout the surface of a pore, because there also concentration is changing. So, here this is 2 pi r delta z is the area, right. R is radius of the pore which is constant. So, 0 to L Ca z, because concentration is changing with z times delta z which is dz, right, divide by the maximum rate. So, here it is mentioned based on surface concentration, rate is based on surface area, otherwise you can write K times pi r square L, right, based on the volume of the pore, choice is yours. So, Ks times 2 pi r L times Ca s, that is the intrinsic rate, right. So, this is not, this is constant, either you define based on the volume or you define based on surface area or mass, same expression. So, either you do this integration, the another option can be, because you know at steady state same moles will transport, right. If you remember, if you recall your diffusion equation, we have written pi r square d dCA by dz, right, input minus output minus discipline. So, if you say that there is steady state, so whatever the moles which enters at pore mouth, same will go inside and same will react, right. So, another thing, instead of doing this, one can do it like this also, That is, just evaluate dE dCA by dZ at Z is equal to 0, which is your pore mouth here, right. Because whatever the moles which diffuse at this condition, the same moles will go the inside and they will react. Steady state, there is no accumulation of mass or reactant species in the pore of a catalyst, right. So, if I am able to know what is the value of dE dCA by dZ, this is what written here, dE dCA by dZ, and evaluate that at Z is equal to 0. That is, you have already the concentration profile Ca by Cs, right. Ca by Cs we have already defined like this. So, this is your Ca by Cs, cos hyperbolic phi 1 minus Z by L divided by cos hyperbolic phi, right. So, differentiate this equation and you will have the concentration in the form of sin hyperbolic phi divided by cos hyperbolic phi, right. So, this is what shown here. So, evaluate dE dCA by dZ at Z is equal to 0 multiplied by the flux, because this is the flux, multiplied by the area of the pore pi r square. So, this is the moles which have been transported into the pore, or this will go inside and react whatever the concentration profile, right. So, either you do from this, from here also you get same expression, because this is the Ca by Cs. So, your Ca is simply cos Cs times cos hyperbolic phi into 1 minus Z by L divided by cos hyperbolic phi, right. And once again you integrate this, it will give you some function of sin hyperbolic, right, and put your limit which is from 0 to L. So, again you will get a function of sin hyperbolic phi divided by cos hyperbolic phi, which is tan hyperbolic phi. So, this is what shown here, dE dCA by dZ, Z is equal to 0, evaluated at Z is equal to 0 times pi r square divided by k times Cs times pi r square. So, here it is based on volume, choice is yours, as I said, right. So, this is pi r square, L is your volume of the pore. So, rate constant is based on this k volumetric rate constant. If you define it based on surface area, so it will become Ks Cs times 2 pi r L. So, I have already told you that k volume is 2 times Ks upon r in the last lecture, right. So, accordingly you can write the expression. So, once you differentiate this dCA by dZ, because already you have the expression for Ca. So, this gives you Cas, differentiation of this expression which is here, cos hyperbolic phi 1 minus Z by L. So, this gives you Cas which is already there times dE phi sin hyperbolic 1 minus Z by L. Differentiation of cos hyperbolic phi 1 minus Z by L will be phi sin hyperbolic 1 minus Z by L. Okay. So, other terms are already there. So, that have been substituted in this equation, and then you just see here Cs dE phi sin hyperbolic phi 1 minus Z by L, put Z is equal to 0. So, this goes, right, this vanishes out, and the other terms which are written, I would like to write them in the form of L under root of k by d, right. So, phi square is L square k by d. So, we have just introduced the term which is already the L is here. So, we have added and divided, multiplied and divided, right. So, L square k Cas divided by d. So, one Cs here also in the numerator. So, cancel, right. So, what is this value? So, this is your phi and this becomes your phi square L, right, L square, this is k, and this d if you take, it is in the denominator now here. So, this is L square k by dE this. So, this is your phi square, right. So, phi divided by phi square. So, your effectiveness factor for a cylindrical pellet or for a pore is tan hyperbolic phi divided by phi. Okay. So, this is the expression for effectiveness factor in a pore of a catalyst which is cylindrical pore, right. Let us see now the same expression or similar expression derivation for a spherical pellet, right. So, for a spherical pellet also the same approach, because the definition is same. So, actual overall rate divided by rate in the absence of diffusion resistance, that is global rate divided by intrinsic rate. So, whatever you know now, global rate is defined based on this, right. Whatever your understanding, you know now that global rate is the rate which is measured at the condition which you have actual concentration profile, right, inside a catalyst pellet. So, there is a gradient of concentration because of the diffusion resistance, and we need to identify that. So, in that case, your global rate R A is defined, if you write in terms of the flux, again choice is yours, right. So, the first expression I told you, you define it, integrate the expression, right. So, global rate, because concentration is changing. So, 0 to R, how does it change, right, and you know the rate of reaction. So, that will be K times whatever the C A concentration variation, rate of reaction I am defining per unit volume. So, 4 pi R square d R, right. This is the global rate, but I said that whatever moles comes to the surface because of diffusion, the same will go inside and react chemically. So, again I can write this global rate by d effective times d C A by d R and evaluate that at R is equal to capital R, right, at the surface of the pellet, or lambda is equal to 1, right, and multiply by 4 pi R square, right. And this is what shown here, that 4 pi R square, because it is flux, times whatever d C A by d R, and because I told inward R, it is going, concentration is decreasing from R capital R to center. So, positive sign can be defined here, right. So, that is what calculated at R equal to R. So, you know now d C A by d R concentration profile, or you can write it in the form of dimensionless parameter, because you have already done that. So, d C A by d R can be written in terms of lambda, that is what the d psi by d lambda, right. So, that definition if you write, so your R gets cancelled. So, 4 pi R d E d psi by d lambda evaluated at lambda is equal to 1, right. So, now calculate d Ci by d lambda from your expression which you already gotten here in the form of C A by C S, right. So, calculate d psi by d lambda or d C A by d R, right, and substitute it. So, very simple expression. So, differentiation of that equation. So, d psi by d lambda evaluated at lambda is equal to 1 is simply your phi cot hyperbolic phi minus 1. If you solve and take the limit, then this gives you phi cot hyperbolic phi minus 1, right. So, your rate is simply R A 4 pi R d E C A S and substitute the value d psi by d lambda. So, phi cot hyperbolic phi minus 1. So, this is your actual rate, right, global rate. So, which you can do from here also, one can check just for your understanding or just as an exercise, you do this and get the expression after integration, right, that is just integrate 0 to R K C A 4 pi R square d R and check, right. So, global rate is this, intrinsic rate already you know, because it is evaluated based on the surface condition. So, either definition, whether you define it based on surface area or based on the volume or mass. So, here it is taken in terms of mass. So, K dash times 4 by 3 pi R cube is the volume of the pellet multiplied by density of the catalyst. So, this becomes mass of the pellet. So, basically K dash times rho c times this can be written in terms of K V based on volumetric rate constant multiplied by the 4 by 3 pi R cube, right, that you know, or that is also equal to 4 pi R square surface area rate constant. So, this is what the intrinsic rate or maximum possible rate for the isothermal case. So, when you take this ratio and simplify again, because we want to write this value in terms of phi, right. So, phi is defined R under root of K by D for first order reaction. So, just this expression will give you something like K dash rho c times R square divided by d E R. So, this is what we want to write in the form of phi square, right. So, this expression is your phi square for the mass rate constant basis. So, K dash times rho c is your K surface volumetric rate constant, right. So, that can be written. So, if you simplify this, so your eta comes out to be 3 upon phi square times phi cot hyperbolic phi minus 1, right. So, one can simplify the expression now for strong diffusion resistance. So, now you have seen two cases for cylindrical pellet or pore, eta is 10 hyperbolic phi divided by phi, right. So, how will you interpret, because eta is your effectiveness factor, right, and eta is something which is in terms of the resistance which is dominating in the pore of a pellet, right, and that can be defined based on eta or phi, right. If the diffusion is very strong, so phi is greater than 3 in this case, suppose for most of the cases, right. So, phi greater than 3 or 5, this 10 hyperbolic phi approaches to 1, right, because you see that value, right, when phi is very large. So, 10 hyperbolic phi approaches to 1, just right 0.999 say like that. So, eta is just 1 by phi. So, this shows that strong pore diffusion resistance case, this effectiveness factor is inversely proportional to the value of Thiele modulus, right. Thiele modulus is simply representing the resistance, right, a kind of diffusion resistance which is dominating in the pore of a catalyst. So, for strong pore diffusion, this is like defined like this, and when phi approaches to 0, low value of phi or less than 3, right, or phi 1 suppose. So, then 10 hyperbolic phi approximates h phi. If you just calculate from calculator the value of 10 hyperbolic 0.99, 0.03. So, it is similar to the value 0.03 like that, right. So, approaches to phi, that time what will happen, eta approaches to 1, right. So, and what phi represents? Phi is representing the kind of diffusion resistance in the pore of a catalyst, right, and we want a kind of this thing, right, because your rate will be high when there is the minimum gradient of concentration, right, and that can be defined because you know now phi. So, phi is something like, if I just take this case, L under root of k by d, first order reaction, right. So, it means you make and you have to make your phi small, because phi is a term which is representing the contribution of diffusion resistance in a catalyst pore, right. So, you have to make your phi small in order to get this eta approaching to high value or 1, right. So, it means you have to make your pellet small, right. So, L is a representation of that characteristic length of the pore. So, basically later on I will talk that L is V p by S x, volume of the pellet divided by the surface area of the pellet, right. So, your pellet should be smaller in size, characteristic size of the pellet should be small, that is one thing. Second thing is that k dependency, right, because you need your phi small. So, when your k is very high, that is rate temperature is very high, k is a function of temperature. When rate constant is very high, then chances are there that diffusion may be dominating, right. So, that is diffusion control. So, temperature should be a control when you look at the kinetic study, right. So, kinetic control study should be generally done at a lower temperature relatively, right. Otherwise, your if the temperature is very high, then it may be possible that diffusion may be governing the rate, right. And diffusion is a design of the pellet, you have to design the pellet accordingly to make the diffusion coefficient high, right, wider pore, right, or a defined pore structure. So, this is what the interpretation for Thiele modulus. So, we have to minimize this diffusion resistance in the pore of a catalyst. So, accordingly design a pellet suitably, and the same thing has been defined here. When you have a effectiveness factor phi which is more that is for phi greater than 20, then eta is simply because that time your cot hyperbolic phi this approaches to 1, right. So, this simply because phi is very large. So, compared to this phi square, that is the phi minus 1 which is here, the cot hyperbolic phi will approaches to 1 for large value of phi, right. So, then your this phi minus 1, because phi is very large. So, we just write approximate it to phi, right, and so that time your expression that is eta is simply 3 upon phi, because this phi and this phi square. So, this gives you just this value, right. It is just a simplified form of expression that for large value of phi, then phi cot hyperbolic phi minus 1 that approaches to approximately phi, right, and therefore, the eta is 3 upon phi strongly, that is diffusion controlled resistance, right. and vice versa will be the second case, that is when the phi is very small, then this number can be just written approaches that eta will approach to 1, but eta cannot be 3. So, basically the phi definition in that case is just r by 3 under root k by d, right. So, that is there are different definitions which are available. So, depending upon that value, that when this phi value is very low, so eta approaches to unity, right, rather saying 3. So, this is what the definition of effectiveness factor, but we have written now either in this form or in this form, just 3 upon phi cot hyperbolic phi minus 1 upon phi, or 3 upon phi square phi cot hyperbolic phi minus 1. There are some other definitions also available in literature to define phi. So, accordingly your eta definition changes, right. So, basically here if you see I said phi is equal to r under root k by d, right, where this whole term is your volumetric rate constant k v. When you write it based on surface area, it becomes k s times S A times rho p, right. When you write it in the volume, it is simply k by d based on volumetric rate constant. S A is your BET surface area, that is what I have discussed, right. So, this is the BET surface area meter square per gram, this is gram per centimeter cube, right. So, this becomes meter square per meter cube, something like that, right, or area divided by the volume, right. So, that is the rate of reaction which is based here on the unit which is. So, depending upon that what that I discussed earlier, k dash, right, and k double dash, that is this multiplied by the mass of the catalyst will be equal to k double dash time multiplied by the surface area of the catalyst, not the BET, right, total surface area I am saying, and that will be equal to whatever the k volumetric times the volume of the catalyst. And now very easily one can write. If you define, so generally if I write here S by W, so that is your BET surface area, right. So, if I write k double dash, that is this k, or in other words k dash, if I write, that becomes k double dash times S divided by W, surface area per unit mass of the catalyst when we write, right, it has the unit. So, that is your SA, right. So, k dash is equal to k double dash times this thing. Same thing when you write in this form, then this is mass per unit volume of the catalyst. So, that is your density of the catalyst, right. So, one can very easily correlate these terms, or one can have a relationship among them, because I told you that R A triple dash, which is rate of reaction per unit volume multiplied by the volume of the catalyst, is equal to rate of reaction per unit mass of catalyst multiplied by the mass of the catalyst, is equal to rate of reaction per unit surface area of the catalyst, or double dash multiplied by the surface area of the catalyst. But when you report surface area S A, that is S by mass of the catalyst, right. So, just take care of these units. So, here this is known as V p by S x, basically a characteristic length. So, suppose you have a spherical pellet, then the volume of the pellet is 4 by 3 pi r cube, right. So, sometimes this L is known as characteristic length defined by volume of the pellet divided by external surface area of the pellet, right. So, for a spherical pellet, the first case if you see, so 4 by 3 pi r cube, this is the volume of the pellet, and surface area of the pellet is 4 pi r square, right. So, this characteristic length comes out to be r by 3, right. Same thing for cylindrical pellet, if this is for a spherical pellet, if the cylindrical pellet, so what will be the value? V p pi r square into length, right, volume of the cylinder, surface area 2 pi r L. So, this becomes r by 2, right. So, sometimes we define this L, which is I said in the case of pore it is pore length, but in rest of the cases it is based on the characteristic length of the pellet, right. So, that can be defined, and same thing for a slab or its rectangular geometry, that will be depending on the thickness and the whatever the this plane on which through which the diffusion is taking place. So, area into that depth, right. So, finally, it becomes the thickness of this slab. So, this L is the thickness of that slab through which the diffusion is taking place, right. So, now I have discussed about the effectiveness factor. So, one can see that for a spherical pellet or any pellet in fact, the effectiveness factor eta, which is here as a function of phi, that goes like this, right. So, this value which is at a smaller value of phi, that is what I said initial value, the eta is nearly 1, approaching to 1, towards 1, right. So, that indicates that the diffusion is not dominating, rather diffusion resistance is not dominating in the rate of reaction, right. So, that is for a smaller value, but when the phi becomes large like that 5, 7, 10, 20, right. So, that time the diffusion is dominating. So, that is known as internal mass transfer controlled reaction or diffusion controlled reaction, right. Also if you look at here, also you can interpret that when the order of reaction is increasing, the dominancy of diffusion resistance is dominating, right, because it is, I told you phi is r under root k Cs to the power n minus 1, right. So, for first order reaction the concentration is not there, but for other cases the concentration dependency will also be there, right. So, because the concentration if it is high, then you will see some kind of resistance dominance. So, for 0 order it is on the upper side, for if you have same phi value. So, you can see here this and this. So, effectiveness factor is higher in the 0 order reaction compared to a second order reaction or first order reaction, right. So, that is another interpretation, that the concentration will also affect the rate, right, for the diffusion governed rates or reactions. So, I stop here and we will continue at next time.